Thank you, Luis. It's really nice to see that how you organize the event. It's mixing exactly the research entities and everybody else to show what they're presenting of all the data set of LiDAR, and even some commercial companies and even service contractors here with the booth. So this is, I think, it's a really nice approach for the event, and I really suggest you, I congratulate you, and I really suggest you to keep going in this way because it's make the community grow really well. So, good morning, everyone. My name is William Kim. I'm the responsible for the airborne sensors and mobile mapping systems at Hexagon Geosystems for Latin America. And today I'm going to present a little bit of the experience that we are having from our customers who are using our airborne LiDARs, and how to make optimal selection between the multiple LiDAR technologies that are available, and to choose properly from that, and what multiple parameters that to allow that the select sensor help us to achieve the specific result that we want. So, but first, I'd like to first introduce who is Hexagon. So Hexagon is that Swedish company that initially started on the metrology business, and in the past years I started to acquire many measurement companies in the market, and from that they start to give us a better portfolio on measurement from macro to micro and even nano. So, for example, in 2005, Leica Geosystems was acquired by Hexagon, and this entire portfolio was integrated to the Hexagon solutions. And many other companies have been acquired, like Sigma Space, that is the owner of the SPL technology, Novatel, and many others now part of Hexagon. And taking the best of each company that has been acquired, Hexagon start to form sensors, software, and autonomous solutions with one purpose: to empower an autonomous future to the industries. So we moved from the efficiency going to automation, and obviously with autonomy is the next logical step. So is to let the technology work for us, think for us. So one simple example that we have on autonomy that we use in our daily routine is Spotify. Spotify learns the music that we like, create playlists, and analyze not only the singer, the band, the genres, but analyzing the sound wave footprint autonomously create us this new playlist that we want. So that's why we are focused on autonomy, to achieve efficiency, achieve productivity, to achieve quality. So this slide here shows exactly what Hexagon is doing right now. So we have, in the past years, we have acquired several sensor solutions. Then in the next years, we start to acquire software solutions to extract the unique value of the sensor data. And with integrating these two solutions into an autonomous solution and aggregating our core capabilities of reality capture to get the physical information, positioning, so we know exactly where they are and when they are at any time, with digital and simulation, so we can recompilate the multiple real-world scenarios that we can do it in a virtual environment, location intelligence, so we can have situational information in applications, and autonomous technologies to have autonomous processing. So combining all these solutions and core capabilities, so Hexagon have what we call the smart digital reality. So it's to have a digital replica of the physical world, its process, its place, exact everything to have the ability to use machine readable data and to let it available to the power of the algorithms that most of you are working, in fact. So with that said, so going back to the topic of the presentation, so optimizing LiDAR technology selection. So when I go with my customers most of the time, I usually do two questions. The first one is what they need, what they want, so I can indicate what is the best solution or the best sensor solution for the job that you would like to do. And the second question is a little bit tricky one, because it's, so what is the accuracy level that you would like for the job? And most often the answer for this second question is, I want the best. But exactly, what is the best in this case? So at this very early stage of the communication that we have, we need to to think exactly in several parameters, like, for example, what is the end use? It's only metrics? It's the guy need only this information of tree heights, or they also need the model tree structure? Or, for example, what are the expectations that he has? So they only want from the data set the results, they only want the trees, or he really wants a topography at high resolution on the ground. And also we also need to think about it, the constraints. So more and more we have these constraints, mostly on the economical side. That's going to be the cost, what is the budget that we have. But right now it's raising up another constraint, that is the legal one. That, okay, so can we public this data that we have to everyone at high density? But sometimes it's not possible. We just can public this to everyone at a lower point density. So the idea with all these parameters, so it's to really help us to find the right tool for the job. So we have multiple LiDAR technology in the market. I'm going only focus on the two technologies that Hexagon provide. It's the single photon LiDAR and the linear mode LiDAR. So the table here expresses some of the main common parameters on the LiDAR technology that everybody looks to select what is the right tool. So for an example, we have the pulse rate of the LiDAR, the field of view, the number of returns that we have per laser, typically the laser output, how many points per second it extracts. We assume here 3 points per pulse out. Also, they have waveform data recording, what is the scan pattern that they have, the accuracy, of course, what's the root mean square error in vertical, the type of wavelength that is used, the laser divergence, and the typical fly height. So we have here 3 columns. The first one on the left, is our linear mode, the last generation. It's called a Leica terrain mapper. It's one of 2 million points. So we can see here that typically we have, for 3 returns per pulse, we have around 6 million points per second. It's integrated waveform data, oblique scanning. We have a very high accuracy data set, and it's working with the 1064 nanometers wavelength. And for SPL technology, we have here 2 columns. One is, I think, the most common that everybody's know at the moment in the market, is our standard angle. It's with the standard 30 degrees field of view. So we have the standard 6 million points pulse rate, up to 10 returns per pulse. But the interesting thing here is that the laser optical output, as you can see, and we have heard from yesterday some presentations, that it's a very low energy consuming, but even with the lower consuming than the linear mode, we have much more points based on the array that we have for the SPL system. And what we are doing right now, based on the experience that we are having from SPL in the last year, we are moving to a new generation that we are still studying how to make approach to the market, that it's a wide angle system that we reduce a little bit of the pulse rate, but we increase the field of view from 30 to 60. So this gives us a much more coverage area, can lower the cost, but of course, as a result, we have a little bit less points per square meter. So let's go see a little bit more about the single photon LiDAR system. So this SPL100, only in the last year, has been acquired more than 120,000 square kilometers in US and Europe. And based on this productivity, to maximize this productivity, that's the reason we have study and start initiatives to increase the field of view, because we have noticed from our customers and from the market that sometimes this high density point that we are achieving with the standard SIGO PL is not required. They can use a little bit less point density, and for that we started with the 60 degree of view. So we increase almost double the swath coverage and reduce from 10 points, 20 points per square meter to 2 to 5 points per square meter. So this slide shows a little bit more this difference between the two approaches that we are promoting at the moment. So in green we have the standard configuration, which is a high point density system, built with around more than 25 points per square meter. We have basically a typical productivity flying at 3,750 meters above ground. We can achieve around approximately 20 points per square meter, but our productivity is around 600 square kilometers per hour per flight. And this, we have 2 kilometers swath coverage with this standard system. And as I mentioned, with the single photon LiDAR with this wide angle field of view of 6 degrees, we are increasing to have flights at 4,300 meters above ground, when we can achieve, of course, a little bit less point. We are talking about from the minimum in the nadir area, around 3 points per square meter, and on the edge of the field of view, 5 points per square meter, but we can really increase the productivity going to almost 1,300 square kilometers per hour. That we are going to use is not anymore 2 kilometers, but almost 5 kilometers on the swath coverage. So, and how we can achieve this kind of partner or the point density that we are using with the wide angle? Basically, we just optimize the scanning that we have from the forward and the back scan that we have in our oblique system. And in the left figure, we can see the pattern that we have with the standard system, that we have a lot of dense points between an overlap. So optimizing the speed of the scan, so we can also have much more homogeneous areas, and this way we can achieve this productivity. So this is an example that we have with this new wide field of view with the 5 kilometers swath. So this is one of the examples. We have here also the intensity of the data and the fusion of intensity and the classified points. We also have here with the standard field of view, that is with the 30 degrees, and it's for the high point density. We have here in the extremely mountainous areas. This is in Hawaii. It was flown 2 years ago. And as you can see, there is a very heavy vegetation here. And if you notice here, there is a little white line here. This is a waterfall in this place. So we can imagine from this little line that we can see that starts here and goes up to here, how steep is this terrain. But one interesting thing that we got from this data set is when we did a 1 by 1 meter cell on this area, at least on 9% of these cells, we have ground detections on them. So this is the one profile section with 1 meter thick of the data set of the Hawaii, so we can really see how is the characterization of the ground, and even how is the canopy of the vegetation over there. And this slide is really interesting for me. It's one research that was done with and this is an extraction from this video lecture. So they did a very quick comparison on productivity about when they use as a baseline 24 points per square meter. So with the standard SPL with the 30 degrees field of view, they are flying almost at 4,000 meters above ground with the 2 kilometers swath coverage, and the productivity they are achieving is going to be around 607 square kilometers per hour. When comparing with the linear mode sensors, if you take the latest generation of terrain mapper, we are talking about flying at 2 kilometers height with 1,500 meters swath coverage and with a productivity of 275 square kilometers per hour. Now, if we compare it with the old generation of the linear mode, like we say old because we have improved it, we are talking about to achieve the 25 points per square meter, you need to fly at 1,200 meters above ground, and your swath is only 640 meters, and your productivity is around 9 square kilometers per hour. This is a really interesting information too, so you can have it so on the productivity side, but it's also important for you to understand how much time you need also for processing. So we can compare, of course, we have much more data, we are capturing much more area, so we are having here we're starting to have some with the standard IT, if I want to say like that, we're going to start to struggle a little bit on the processing time. So with the oldest technology of the linear mode, we have 4 times the flight time. If you go for the latest generation of linear mode, we are talking about 20 times of the flight time to get this data processed. But if you go to an SPL, we are talking about 80 times the flight time. So the IT, it's a huge differential part when you are capturing this kind of data. When you need to take care of this information, of this parameter too. It's not only taking care of what is the LiDAR system, what the parameters that they have, but also taking consideration these parameters of processing time, so when you have the data available for you to start your analysis. Okay. So going forward to the linear mode, so sometimes we need to have an even distribution point. This makes a lot of difference when you do some analysis. So, and when we have this kind of case, we suggest that a sensor that can have a constant density mode available is much suitable. So why that? Basically, with this constant density mode, what the system does is to have the same pulse rate frequency as in the constant mode. So we have the highest, but as long as it's approached to the edge of the field of view, it starts to automatically reduce the pulse rate frequency, so we can have it a very even distribution partner of my points. So what is the benefit on that? Basically, we have this very nice point distribution. It's going to be really good to the algorithm that we use, but also we have a better processing time because we're talking about approximately 35% less points than when you use the highest or the constant pulse rate mode that we want to have the highest density points. So we have a little bit more space on the nadir area, but in the field of view edge we start to have a lower space between the points. So this is one of the examples why we use this constant density point, and also why we use the oblique scan partner, so we can also detect what is the constructions or vertical surface facades or information on the height, so we can also implement into the point classification or automate how do we classify this with this information from the oblique partners. And not only in some flat or not rolling hill surface, but also in high steep terrain, This area is in Santis, Switzerland. It's one of a really mountain area, nice mountain area, and they have some buildings on the top, so we can also have a very good, take some very nice photographs over there. But interesting part here is that we have some surface movements of 2.14 centimeters on the total hash. So this is one of the examples applied to the forest from the terrain mapper, where we can see here within this 40 meters thick section profile, we see here on the left side the conifers, and we can see another species, it's going to be deciduous, and small. We want this even point distribution, and if your budget allows that, we have a lot of money, but it's not most of the case, so you can also go with this LiDAR mode. In the case of the standard SPL system, we are talking about covering of really large areas, some regional area, but we really want high point density in this case. And we want to have the metrics of the structure from this high point density. Now, if you want to cover a really wide area like continental, statewide, so you can go for a SPL with the wide field of view, where you don't need so much point density, there are not so much structures for you to study, so we can go for this kind of system. And of course, the cost of the collection is much lower. So, I'd like to thank you, everyone.